dot is less than 0. And obviously this is a sufficient condition in the sense that if the system is quadratically stable, then we'll say that the system will be robustly stable. Means the uncertainty that you have taken, those are admissible, and system remains stable within that range of the uncertainties. But the converse is not true in the sense if the system is not quadratically stable, still the system could be robustly stable, right? So we are considering a smaller set or smaller area from that whole robust stability region. So let us see some of the approaches for uncertainty modeling. So given a system model x dot equal to x, given that this a value takes from a set of a, then this a or this x dot equal to x can be modeled using two approaches. One we call as norm-bounded model, in that we take a nominal value a plus the uncertainty portion we embed within this with the normalization that norm of ft is less than equal to 1. So this ft could take smaller values than this one, but still it captures the uncertainty or variation in the system parameters. In that this d and e are the exploits the structure of the uncertainty. Maybe that you have an uncertainty in one of the element of a, then this d and e you can choose appropriately so that that structure is exploited. The other one is that the polytopic model. Polytopic model, it consider a convex hull of set of or vertices of the matrices, that we take this AIs are known but they are different, and at a moment this A value will take combination of these vertices. So this is a convex set. This is an extension of polyhedra concept for the matrices, and if we can express that this will take within this combination of these vertices of the matrix A comprising of AIs, and say that this is alpha AI, given that alpha I always take greater than 0 value, greater than equal to 0 value, and this remains within 1, then this represents a convex set. And if the set of A matrices that lies within this convex set, then we can represent or do the stability analysis with respect to each of the known vertices of this polytope. So we'll see one of the case for the quadratic stability of such uncertain systems. We consider the norm-bounded system, that a plus dfte, given that norm of ft is less than equal to 1, and let's consider the a takes this structure: -1 plus delta 1 minus 2 plus delta 2, delta 1, delta 2, delta 3, delta 4. These are uncertain, and -1, -2, 3, -5, these takes nominal values of these elements. Then we define x transpose px. This is standard for linear systems. Obviously there are variations in few cases, but since for nominal stability we choose this v, so we'll carry on with this, and then we'll get an inequality like this. You can see here a is there, d is there, e is there, so a, d and e are there, and this norm value of this ft, this has been replaced. This ft is not there, which captures the uncertainty of the variation. This can be expressed as an LMI, can be solved efficiently for given A, D and E matrices, and if you get a feasible solution of this, you say the system is stable. The AID condition corresponding to this is that you equate it to a minus q, or q is a positive definite matrix, given that this minus q makes it negative definite, and solve for p. So this one you can get a solution using that AID, but mostly we will discuss the LMI solution today. Then other problems also you can frame in as an LMI problem. For example, the pole location region, or you have to place poles in a certain damping region. Think of this, we get that poles are located within the shaded area with that cos theta equal to some zeta. Then all the poles will satisfy minimum damping rate of that cos theta equal to zeta. It could be overdamped compared to that zeta value, but it will satisfy that minimum damping and won't have a damping lesser than this value. Also, you can specify that its decay rate could be faster or satisfy e to the power minus alpha t at least. So these problems also can be framed as an LMI problem, and those solutions are available. For example, this is a solution for H infinity design with pole placement constraints, right? So we'll look briefly how it looks like when you consider a state feedback control design with pole placement constraints. So see that theta and alpha, these are the two parameters corresponding to the shaded figure. And here is alpha and here is sine theta and cos theta that relates to the theta values. And the sigma equal to x plus by, where x and y are variables, matrix variables that you have to find out by solving this inequality for given alpha, theta, and A, B matrices. So that would be a state feedback control design by satisfying the pole placement constraint. So that way, many other problems also we can frame. The H infinity state feedback control design. For H infinity design, we consider that this is the plant. It has disturbance input W, and it has that output or desired output Z infinity. We want to design a controller K. This is the output Y, measurable output, and giving feedback through again K or controller K, and generating the input or controlled input to this controller input to the system, so that from this disturbance to this desired output Z, the transfer function or the that is called the infinity norm of the transfer function that gets minimized. So many problems in control that can be framed in this, and for that, or for state feedback control U equal to Kx, the H infinity design specification can be given as this: minimize gamma so that the transfer function from this W to Z and its infinity norm is less than gamma, so that the effect of this disturbance on this Z will get minimized. And this is well known bounded real lemma, that gives a result that if you satisfy this matrix inequality, linear matrix inequality, and solve for x and y, these are the two variables for this given system. The system is in this framework given the A, B, W, and BU corresponding to different inputs and outputs. Then the state feedback controller y equal to x inverse that will minimize this gamma. So this is well known result corresponding to the H infinity control design. And as you have seen how we can solve an LMI, we can augment such several of the performance variables or performance objectives and solve in a single framework or using a combination of elements, so that multiple of the objectives can be satisfied. For example, the pole placement constraint, the H infinity design, all these problems or all these performance criteria can be augmented or can be made together at a time by solving one optimization problem. Then for state feedback, this comes up as an LMI problem that we have seen some of the LMI criteria. When we come for static output feedback control design problem that we discussed initially, then let us look at if we try to solve the problem using the same framework, using the Lyapunov's direct approach or the quadratic stability, then what the problems are. So we consider instead of state feedback y equal to cx, and we want to replace that ut equal to kcxt. Then using v greater than 0 and v dot less than 0, the conditions are come up like this. The first one is that we have to replace a plus bkc, a by a plus bkc, that transpose b, and as you expand, this looks like this. Now for this problem, see that this a, b and c, these are the known matrices, and you have to find a p and k satisfying these inequalities. So this is not an LMI problem because multiplication of the two unknown variables p and k, these two multiplication of these two are involved. So these problems often called as bilinear matrix inequality problem is NP hard to solve due to the term of PBKC, and it's not an element. Then if it is not an LMI, the solution would be that we have to approximate or approximately express this as an LMI, then find a solution and carry on or move on. One way is that solve that iteratively. So this is one ILMI algorithm. I'll show the reference for this. The closed loop system is stabilizable by a static output feedback if and only if there exists a real number alpha greater than 0, here is alpha, and matrices p greater than 0, x greater than 0, and k satisfying the following matrix inequality. If and only if means this is necessary and sufficient condition, and we solve it iteratively. Obviously, the problem with iterative solution is that the convergence is not guaranteed. So once convergence is not guaranteed, that does mean that you start with different initial values and see whether it converges, and if it does not converge, then you are helpless. So the iterative LMI, or solving it iteratively, that goes through this. This is an algorithm. Obviously, there are other ways to solve this, means expressing it as an element, but we'll discuss or we'll use this algorithm for designing the controller 2D. So given system A, B, C are given, then find a ARE solution for given R equal to I and Q equal to identity. Then assign this X as P. So then X equal to this solution of P means this X becomes known. Then our variable is P, then this will be an LMI problem and you can solve, right? And for that, obviously this K has to be known as well. So once this X is assigned, then K is also assigned, then solve for P, then go for next iteration, fix this P and solve for this X, or update the X with the P. So that way we can iteratively try this. And obviously using suit complement, this one can be expressed as this element, and try with an X value, then find a P and K value, then check whether K is stabilizing output feedback gain, then you stop, otherwise update that X with P value, till then certain convergence is not ensured. So this norm will be difference between Xi and Pi. There is a mistake. Difference between Xi and Pi should be less than some specified tolerance value. And once these two converges, then and you don't get a stabilizing feedback, then you are helpless and not able to design an output feedback gain. But for the example that we took up, for that we obtained solution, or we could get or arrive at a solution, and that we used successfully. Then we'll see the application side, or how such problems can be defined for an induction motor application, and how that can be experimented with. So we'll see these four set of problems. One is that first one is the bifurcation behavior. Bifurcation particularly comes from that nonlinear system perspective, and since the indirect vector control of induction motor, or when you say and induction motor dynamics, that is nonlinear, so it demonstrates several such nonlinear dynamics behavior, and still that can be analyzed or visualized or can be studied through the linear system analysis, particularly that corresponds to the validation of the linearized model, that still we can validate the nonlinear dynamics through the linear analysis and the linearized model is validated, then you can go for control design. So we'll show the several of the PI controllers that are used in indirect vector control of induction motor, how the robust designs can be made for that. Then we'll see how the decoupling problem in such induction motor control problem that can be defined and solved, and we'll show how dynamic controllers can also be designed. So these are the induction motor parameters. So I won't go through this. Just few references that suffix s corresponds to the stator resistance, suffix small r corresponds to the rotor resistance, kpd, kpq, kid, kiq, and kp omega, ki omega are the there are three loops, and corresponding to that 3 pi gains are there, and omega corresponds to the speed. So this is a speed loop control. There is a reference speed, and you try to match up that speed using several of the inner loops. I will not go to details of the vector control or why vector control, but rather we'll work on how the model is from the control perspective and how you can work out on that. So if you look at the induction motor model, so this is a fifth order model. People use a reduced order model as well, neglecting the first order dynamics, means third order model and so on. But this, we have taken up this third order model. This is nonlinear. Still we could have a solution for this. Sorry. So there are 5 states. If we identify IDS is the current in the direct axis from the stator side, side air flux linkage on the direct axis at the rotor side, psi keyword, and omega is the speed. These are the 5 states for this. The torque equation is this, which drives the speed, and you can see the first 4 states are involved in developing the torque. And this is another parameter that is important from the induction motor model. This is sigma, that is equal to RR by LR, and this particularly these are the internal parameters of the induction motor, and those are subjected to change based on different environmental condition. For example, as you run the motor, this RR or the resistance gets reduced once the motor is heated up, right? So corresponding to temperature variations, these parameters are supposed to vary within the model or within the motor itself, right? So this is the induction motor model. And when you try to do vector control of induction motor, then we take or try to do it or try to make it behave like a DC motor. So in that, recollect the torque equation. So it involves the first 4 states, and if you do the vector representation of them, then psi qr and iqs are aligned here, and IDS and psi dr are aligned here. In general, this psi dr is provided the reference signal, and psi qr is kept 0. The reference for this is kept 0. So once you keep it 0, psi qr 0, then this component vanishes. Then using that side year reference that is fixed, that is fixed, or using by varying this side year reference, you can vary the torque component, right? So that is the vector control of induction motor. And in that case, these references are given. Obviously the speed reference will come as another loop, and you have to maintain that these values will be or follows the reference values. Actual variables follows the reference values. So that way, if you look at the indirect vector control scheme, then here is your induction motor. You measure the speed, you measure the currents of the motor, then transfer it to the DQ frame, and here you compare the speed measurement with the speed, take a PI control here, then slip speed is generated, and slip speed, comparing these two, you will get the rotational speed, the omega E, and from there, by integrating, you generate the theta E. And here on this side, if you see, then side year reference is given. Then you get two current loop. One corresponds to the IQS and the other corresponds to IDS. And you can see there are three PI control blocks here. And if you try to map the input and output, then one speed is one output, then IQS is another output, IDS is another output, and these two are the reference input. Psi QR reference is 0, right? And by that, you control the switching of the inverter, which finally controls the voltage to the induction motor. That way, the motor is controlled. So this PWM inverter, if you use a 3-phase power supply, you use a rectifier. From there, you use an PWM inverter to get AC supply to the induction motor. By switching the inverter, you get the varied voltage applied to the induction motor, right? So this is the overall block diagram of the indirect vector control of induction motor, and the objective is that you have to frame this as a control problem that we are trying to do. And we have seen that the induction motor model itself is a nonlinear model. So the overall block diagram, if you represent by removing that supply side, that we generate the VAS, VBS, VCS as we desire from here through that inverter and apply to the induction motor. So this is a simplified diagram of the same. And here you can see that sigma is involved, and we have multiplied a factor, that alpha, with the sigma, so that alpha is sigma hat by sigma, and this would be, we'll call it as a tuning gain parameter, particularly for study of the dynamics. It's not the gain parameter for the controller. Gain parameters for the controller are the 3 PI. This is a parameter that can be tuned or can be changed in the analysis to study with respect to this parameter variation how the system behavior would be. So we take up the sigma hat. We have taken up the variation in the resistance, keeping the inductance phase. And this is well known that with respect to the variation of this alpha, the induction motor dynamics behaves very differently. So we'll see the same in our analysis and how that can be exploited from such a system where several of the inputs and outputs are in. Sure. So with the three PIs, PI control gains, they introduce 3 integrators, so you will have 3 more states corresponding to the 3 PI. So we had 5 states of the induction motor and 3 states corresponding to the 3 integrators. We have defined this way. You can define it slightly differently, but you will always get an 8th order or 8 number of states. And if you replace the state definition x1, x2, x3, x4 in that overall system model, then the system dynamics will look like this. And you can see that there are several of the nonlinearities. Here are x6, x2, these are multiplied, x4, x6 is multiplied, x6, x1 is multiplied, x3, x6. So this is not a linear model. And if you identify the tuning parameter is here, this alpha. And we'll like to see how this how the behavior of the system would be. So since this is a nonlinear model, then analyzing it would be very difficult. So we'll try to linearize it around an operating point and then try to get a linear model, and we'll study how this behavior would be. And I don't know whether you have tried to find a operating point for this system or not, but for a 8th order model and to find an operating point for this, particularly to find an equilibrium point, is really difficult. There is a solution if we go systematically by one solving, starting from the speed reference and considering that the speed reference can be achieved in closed loop, then we can obtain the equilibrium point. And if you find it, try to find it by solving one by one, then the finding the equilibrium point, that comes down to such a problem that these will be the equilibrium point. Among this, we can see that x2e corresponds to the equilibrium point of x2, x3 that is this, x4 is this, and x6 is this, and x5 is missing. X5 is that omega reference minus omega r. So let's go back. X5 is omega reference minus omega r, so its equilibrium point is also 0. So omega r reaches omega reference. And if you look at the first equilibrium point x1e, then this is a quadratic equation, x1e squared, and that defines or that varies the dynamics of the system very differently from conventional linear system. If you solve this, then you get an solution of this quadratic equation corresponding to the x1. And obviously, since there is square root of this and an equilibrium point should be real, so this m square minus 4ln, the real value of this, that defines many things. So as you define m square minus that 4ln component should be greater than 0 to have an real value of the equilibrium point, then for the alpha we get such a bound that alpha should be within this range to have the equilibrium point should be real. And this can be seen that if we linearize the system along the equilibrium point and along any of the equilibrium point, obviously we're taking the varying value of that alpha, and we'll get this x dot equal to gx. This will be the linearized model. So there could be a lower order model if you consider a third order one and fifth order model, and those can be augmented. And these are the other components. So I'm not discussing about this or not expressing or discussing each and every element, but we can see that these control gains are involved in this. And with this, if you see the stability behavior, then stability behavior will show that bifurcation behavior for the system. For example, we seen that the equilibrium point may take a boundary within a particular range of alpha, and beyond that the equilibrium point of x1e will become imaginary. So that is not a feasible situation for a practical system. It cannot take a complex value, and that shows, or if you solve the dynamics numerically, we can see that this gives a bifurcation behavior of the system at this particular point. So these are the different bifurcation definitions: saddle node bifurcation, hop bifurcation, and other bifurcations. And this could be seen by exploiting the properties of this. If a single real eigenvalue crosses the imaginary axis, so we have to find when the real part of the eigenvalue of a particular eigenvalue that crosses the uh, imaginary axis. Then if a pair of complex eigenvalue crosses the imaginary axis, then hop bifurcation happens. For example, the hop bifurcation condition given as where alpha h indicates the hop bifurcation point. So that way numerically you can check for the linearized model, its eigenvalue or its complex eigenvalue, they are changing behavior corresponding to different equilibrium point. And there are several revelations corresponding to this. So we took the induction motor parameter is this. The same model we use. These are the induction motor parameter for an induction motor that we experimented with, and it has 4 poles and other parameters have been measured at nominal values. And as it is the equilibrium point, particularly the x1e, that is a function of alpha, as you have seen. So this becomes, or finding particular crossing of the eigenvalues, that becomes iterative problem, because when an eigenvalue crosses the zero value, then corresponding characteristic equation will become 0, right? And they will get a particular pole at 0 value. And since the equilibrium point depends on that alpha, so this P0 also will depend on alpha, and that becomes an iterative procedure to solve this one for the Kp and Ki values. And iteratively, as you solve, you get a particular bifurcation point. So that way, several of the bifurcation points have been studied. And you can see with the variation in the parameter how the bifurcation behavior becomes prevalent or can be visualized. These are simulation results, and you can see at a particular point, as the alpha value is changed, the behavior gets completely changed for the motor. So these are the different points for the alpha values, and the different Kp and Ki values are taken. I'm not going in detailing how these changes are. For example, here this is indicated, this is hop bifurcation, and this is saddle node bifurcation plus hop bifurcation. Similarly, other cases are there. But you can see the bifurcation behavior in the sense that the behavior of the system or the system state that changes drastically. Obviously, when the changes occur drastically, you cannot do the experiment or see all the bifurcation behavior in a physical model or an induction motor. Obviously, there will be burning out and other cases, but some of the cases can be studied. So we take up this setup. So we have an induction motor connected to a DC generator. This DC generator is taken as a load, so that the electrical loading of the DC generator changes the loading of the motor, and correspondingly we can keep the motor at different loaded condition. There is a speed encoder, the rectifier inverter stack. We use a DSpace to control the switching logic of the inverter, and there are current sensors for the 3 currents for the system, right? The same model have been considered as we discussed earlier. This is a 2.2 kilowatt model induction motor, and the speed sensor has been developed in laboratory. Then these are some of the bifurcation behavior. You can see with respect to load variation, the equilibrium point shifted. But when you change the alpha value as you implement the indirect vector control setup, the bifurcation behavior is visible. Similarly, here also with alpha equal to 2.5 varied from 1.5, the system becomes stable or regulated at particular speed value once again. But if you change it further to alpha equal to 3, then the motor goes to halt situation, right? These are experimental result and particular experimental behavior of the IQS current of the motor. Here also bifurcation behavior is visible, right? So that shows how the linearized model that validates the actual nonlinear system, and the same can be used for control design, right? So once this is we obtain the linearized model of the system, then as we try to control design, then we have multiple inputs and outputs. So we separate out the control gains, kp omega, kp ki omega, then kpd, kid, and kpq, kiq, and as you express them as an output feedback system, then this would look like this. This would be the linearized model of the system, and uh, and this would be the desired output corresponding to the alpha variation, and we want to minimize the variation of the alpha. And then this is the measured output that we try to feed back in this U, and delta W we model the alpha variation as a disturbance. And delta Z we have taken the first 4 states of the 4 currents, the IDS, IQS, and the 2 flux linkage components of the motor. Then linearized model G1, G2, and G3. This looks like this. G1, G2, G3 are the 3 matrices of the A matrix. Obviously, this is a 8th order model. So this is 1, 2, 3, 4, 5, 6, and 2 are here. And you can see the control gains are not there, kp omega, ki omega. Those are separate out. Those have been separated out and expressed as this. B2 is the input corresponding to the pi gain inputs, and delta y will be equal to f into delta y. This is corresponding to the linearized input and output. And if you can see, this takes a restricted feedback structure that we discussed at the beginning, that all the outputs are not connected to the inputs, and there are 6 outputs corresponding to the system, 6 outputs, and there are 1, 2, 3 inputs in the 3 loops. So if we go back to the structure of that block diagram of the control, so see, there are 3 loops, so there are 3 inputs from the 3 loops, 2 current loop and 1 speed loop, and corresponding to each pi, so there will be integral means another state, another state here. So 3 into 2, so there will be 6 outputs, 3 corresponding to the actual value of the state, and another 3 corresponding to the integral value of the state. So there will be 6 outputs and 1, 2, 3 inputs. So this will be a MIMO system case, and again the this is in structured fashion in the sense that this output you are not using to generate this VQS input. Similarly, this error signal you are not using to generate this control output, right? So there are restrictions in that. But the benefit is that we take the overall system. It's not that only the current loop is designed or the speed loop is designed, but we take the overall system and design this controller at once. So that has benefit that the controller design that you do, you can directly apply to the motor and still it works. So this will be the system. You take the states and then output gain matrix, then you get y, then compared with these two output two reference signals comparator. These two will be the reference signals you will provide to the system, and then you use the control gain and generate the input to the system. We use the iterative LMI algorithm as you discussed earlier, and we know the linearized model, so we have the solution for it. So I'm not going back to for how the iterative algorithm works and all this. And sorry, the reference signals that you have taken to be operated at 80 radian per second, we see how the reference signal change. As you change the reference signal, obviously the operating point will change, but for that nominal design, how the controller would behave, that obviously we can explore. And we take side yard reference. Existing design, if you see, then this is only the speed loop design. Current loop design has not been done here, or considered that current loop design has already been done using a separate method. But if you use modern control framework, then all the three controllers are designed together. And often for the two current controls, since CISO designs are adapted, those two gains come out to be same as you design using classical methods. But here, since we are designing all together, obviously difference in the control gains for the two current loops are expected. So that we'll see here that the PI controllers for the D-axis current and Q-axis current, they are different. But if you take up other designs, then they design for the one PI controller and take up the same for the other one. And you can see the proportional gain for the D-axis, that is much larger compared to the Q-axis. Q-axis, obviously the integral gain is other way. And speed loop gain, that is much smaller compared to the current loop gain. Current loops are always faster compared to the speed loops. Those are inner loops and their gains will be higher, so that is expected. So these are Bode diagrams corresponding to the linearized models for the inner loop and the outer loop. Obviously you can take one input output combination at a time, and you can see the difference in between the existing design and the combined design. If you see on the right hand side that the gain is reduced for the outer loop, means that has been made much slower, whereas the inner loop, particularly the IDS one, that has been made faster compared to the other designs. These are simulation results, I am not going to discuss about that. And if you see with the available designs, the motor often fails to get stabilized with respect to variation in speed. But if you use variation in speed reference, still the motor remains stable. And also if you consider the parameter variation, that also remains stable. So this is the situation. Left on is the existing design, and this one is the design using the modern control framework. The omega reference is changed here. Here also it is changed, and here it is changed. So this goes down to 0. So this does not hold up that reference value of the speed, but this one does hold up the reference value, right? So similarly, this one for variations in the parameters or the alpha parameter, so this still remains stable and follows the reference signal, reference speed signal. Often for induction motor control, we have seen that the two current loops are there, the ID and IQ, and they interact by the system dynamics itself. So often it is desired that the D-axis and Q-axis current, they remain separated, and for that decoupling is used. So this is one of the existing decoupling scheme that we use here at VDS. This is the DS current loop. Here a compensatory VDS is used, that is equal to omega E IQS. So that does mean you measure the IQS and compensate the effect of the IQS in that IDS loop. Similarly, you measure this IDS and compensate the effect of IDS in the QS loop, right? So these are uh, existing decoupling scheme, and you can see the effect of the decoupling. The red one is that feed forward decoupling, and blue one is that without decoupling. Without decoupling, the effect in IDS that is much higher, because both the IQS and IDS starts varying at the transient, and their effect together is much more deterioratory and variation is very large. Whereas IDS variation with feed forward decoupling or this decoupling scheme, that is much smaller, or the variation is smaller. If we see the VDS compensation and BQS compensation, then this can be expressed in terms of the states as this. So if we know the state information, we can construct this VDS, BQS and compensate this. And as you do this, obviously we need to have additional arrangement for this compensation, right? So question could be that, can we use this PI control gains without this feed forward compensation, or uh, can we design the controller in such a way that this decoupling can be achieved without this feed forward compensation or additional circuitry arrangement for this? So we define the performance objective that way, that the dominating omega E IDS and omega E IQS are chosen as the performance variable, or for the H infinity control variable, that we want to reduce the effect on this. So corresponding to that, we design the controllers. So you can see this is the current loop, and for that the current gain becomes higher, right? Body plot for the current loop, whereas existing design of others, they give much reduced gain for the current. So you can see that the current gains has been increased now, particularly corresponding to the D loop. And for the Q loop, the gains are much reduced compared to as you designed or as you did the first attempt for the design. The Kp and Ki for the speed loop, that remains almost in the similar range, right? But if you see the existing design, then designs are that this is P gains are almost same, they are same, and there are variation in the I gain for the Q loop. Here the PI gains for the two current loops are taken as same, right? Obviously we won't get the same effect as you do considering the whole design or the performance objective design as it is required for the purpose. So I'm skipping the simulation part, and if you see the experimental results, then the okay, its title has been vanished. The left hand side is the existing design, and right hand side is the design using the uh, robust controller design methods. So you can see here load is applied at this point, and if you zoom in, the speed variation that looks like this, and this one is the IDS variation, purple color. And if you zoom at the speed load applied condition or the disturbance applied to the system, then it looks like this. And right hand side, these are the corresponding variation. So you can see without using extra circuitry, the response is much better, and you can see the IDS variation left hand side and right hand side for the same range. If you expand, then you can see there are lesser jittery or lesser variation or much stable response for the system. Similarly, it can be seen here as well at the bottom side for different other variations. So this is speed positive speed reference variation is given and negative as well. Both variations shows similar effect and corresponding IDS and IQ with respect to variation in TL. Then other problems also can be framed. Other problem can also be framed. For example, as you use a PI controller, I'm going back. As you use a PI controller, so proportional gain that does change the input instantly. And as you change the input instantly, and this is a motor, as you change the current suddenly, the motor uh, gets a sudden load torque change or electromagnetic torque change, and motor tries to get reverse, right? So that sometimes may damage the motor if the variations is very large. So can we develop other control schemes? For example, instead of the proportional one, if you try to apply a dynamical controller there. So we change the scheme like this. So this is a PI controller. Here is your proportional gain. Here is the error. You feed that to generate the input to the system. That is the output of the controller. And proportional gain and integral gain are there. Integral gain is fine because it integrates, and as you integrate a step change, then you will get a ramp signal, so that varies slowly, right? But this proportional gain, as you have step change here, so this is transmitted to the control input as a proportion to this. If you change this slightly, in the sense that this Kp or the proportional gain, that would be a dynamical one. Dynamical one means that could be a first order transfer function, a second order one, and all these. We choose a first order one. Then we have designed this controller. We have designed this first order controller, and corresponding to each and every loop, we have taken a first order controller. First order dynamical controller instead of this Kp. We kept the integral gain or integral portion as it is. Then we tried to reformulate the problem and designed it. So you'll have a changed system matrices looks like this. And I'm not going back how the design method is same, except that the system A matrix, B matrix, and C matrix will change, but it will be in the same framework as we discussed, that output feedback control framework at the beginning. This is again simulation response corresponding to the conventional PI and the dynamical control. You can see the dynamical control for the first one, the speed loop, that becomes slightly faster compared to the conventional PI, whereas for the IQS, this becomes slightly slower for the dynamical control, right? Similarly for the IQS and the speed. Then obviously rather than the simulation result, if you see the effect in the experimental result, obviously you can see the gradual change in the speed corresponding to the PI controller, because demand becomes very faster, and you can see there are overshoot in the speed response. If you use the PI controller, the first one figure is corresponding to PI controller. Second one, you can see that the response is much smoother, no hard demand in the control input, and motor runs more smoothly compared to the PI controller that are conventionally used. So these are other cases for existing speed loop design and compared with the others, and this shows that when controller is switched to the other designs, then it gradually decreases and motor comes to a halt even if there are omega reference. But with this dynamical controller, the speed changes much more smoothly, and if you zoom in, these IDS and IQS, those are also much smoother compared to the other cases. Okay. So that way, several performance objectives can be defined in the same framework, the same method can be used, and the design controller can be directly applied. Obviously, you can combine all these performance objectives and can use at a shot as well. So we discussed robust control design method with performance criteria for memo system, and there are multiple inputs and outputs, and we have seen how it works for an indirect vector control of induction motor. Obviously, there are more cases you can, as I discussed, you can do multi-objective optimization problems, then other machine drives application without sensing the speed, multi-phase machines and wind energy systems. So scopes are huge. These are the if you want to go for more readings, the related papers are these, so you can go through and see. If you have any more doubt or you want to really work out on these problems, these are our publications, so obviously there could be people who have done in similar area, but this is possibly the first application from the robust control theory on that induction motor, considering all the loops together in that multi-variable set. And the first problem, getting a linearized model and framing the control problem, that is much more difficult compared to as you design the control. So that's why initially, or the starting phase, that is more difficult compared to the application phase. These are some of the reference I used in that, and thank you for listening. So I may have skipped many points, but given an overview of how such controls can be designed in a memo setup. Hopefully you enjoyed.
Yes, it was a little bit long, but very informative. I think very useful session we had. Participant side, if you have any queries, any questions, anything to discuss with sir, so I'll have 5 to 10 minutes more. Mic disabled.
Please, if you have any question.
It's from the audience side.
Hello, sir. This is Ravi Shankar.
Yes, Ravi.
Yes, sir, I have one question. How you are taken care of transient response of the proposed systems and its controller performance?
Okay. Transient response means you want to say that
The oscillations in your
this one you want to say the bifurcation behaviors that is
yes, fine.
Yes, this one as it is measured, the currents are measured. So this is the IDS signal, IQS signal. All three are IQS signals at different scenarios, and these are transformed from that three current measurements of the signal using the theta e value that are computed. Sorry. And the case is the load applied. If you can see here at this point, load is applied. So if you consider the experimental setup, then here load applied through the generator. So we switch on the generator load. We connect a resistor to the generator and then switch on the generator load. And second one is that when the load is applied, still it does not change the behavior, right? But if you change the parameter alpha in that indirect vector control loop, then the change in behavior is visible. Even at the same loading condition, the load remains the same, right? So I'm going back to the block diagram. Okay, so you can see this is the motor, and this portion has been embedded within the disk space, right? So here this alpha parameter is changed at that particular point. Let's say alpha parameter is changed from 1 to 1.8 at that particular point, right? So there are variable parameter values that you can give in this space, and this portion, since this is emulated, you can change that value. And the load variation, if you see, then load variation, I'll go back to the experimental setup. This induction motor, this is over this, the experiment is done. This is connected to a generator, and this generator's output is connected to a load. This is not shown. So as you switch on the load or change the resistance of the load, this generator gets loaded. That changes the load condition for this motor. So that way the load is emulated and you get transient response for this. Okay, is that okay, Ravi?
Yes, sir. Yes, sir. Okay. One more. I will add one more question in there. Okay.
Yes.
You're using PI controller over there.
Okay. Yes.
So why not P? Why not other controllers? And why PI only? So what is the significance over there?
So if you see across applications,
because if I use PI controller, there is a problem of oscillations over there.
Obviously.
Yes, okay. So my questions related to that way, sir. How you are taken care of transient if you are using a PI controller over there?
Yes. So it's that not PI controller. Your question is related to the integral part, right?
Yes, yes.
If integral part it induces oscillation, then why you go for such controller, right?
Yes.
So the benefit of integral control is known.
Yes.
The steady state error, right?
Yes.
So
yes.
you try to make the speed reference.
Yes.
Then you have to use an integral controller. It's straightforward.
Yes, it's fine.
Similarly, if you want to do that for IQS and IDS, then you have to use an integral controller. And you have to carry on with that if you want to achieve these references.
Okay.
Derivative is not used from that.
Sure, because there are problems in electrical networks as a noise, so it is difficult to tackle.
Noise gets amplified. Derivative, there will be more amplification of that. Whereas if you use an integral one, then the noise is integrated. The noise gets reduced, right?
Means simply you're targeting to reduce the errors, so that's what you're using PI control.
For that integral is used.
So, one more thing, in your initial slides, you discuss about the robust control strategies based on H infinity controller, and you're talking about something LMIs and all those things, right?
Yes.
Okay. So in
the
that,
same method we adapt here.
Yes. In that, we are going to select some weighting functions over there, right? When we are going to design the H infinity controller.
Okay.
Yes. Okay.
The selection of weighting function is an open issue, obviously.
Yes. Obviously, it's an open issue. Okay. So how you your design, how you proceed, and how you selected weighting functions over there.
Okay. Fine. So obviously control theoretician do that choice of choosing weighting functions, right?
Yes, sir.
And
Because it's a global issue now.
wonder over that how to choose the weight functions, right? But for this application case, we have not chosen the weight functions, right? For this application case, we have not chosen the weight functions. Rather, we have chosen the variables more minutely from the application point of view. For example, if we come to that decoupling problem, then we said that uh, this component is the coupling from the IQS loop to IDS loop, and this component is the coupling from DS loop to IQS loop, right? Then we chosen the performance objective for H infinity control in such a way that this component gets reduced.
Yes.
Okay.
Right.
So then the output that you choose, the desired output that appears automatically. You don't have to choose the weight function.
Oh, oh. Okay. Understood, sir.
You don't have to choose the weight function. Weight functions are chosen when the desired signal is fuzzy, not known to us. So
Right.
we ponder on how to choose these weight functions, right?
Yes. Yes.
But here our objective is straightforward. We don't go for choosing weight functions. Rather, we choose the desired objective that you minimize this.
Yes. Yes.
Okay.
Yes.
But obviously, there are other standard methods for other applications where such objectives is not clear. So you choose low pass filter and high pass filter as the dependent functions. Right?
Yes.
Okay.
Thank you. Thank you, sir.
Thank you. Thank you.
Any questions from the
Audible,
other?
I am audible, sir.
Yes. Yes.
Sir, I have a two doubts, sir.
Okay.
What is the difference between LMI and ILMI, sir? Why we go for ILMI?
Yes. So, LMI is that linear matrix inequalities that is clear, right? I discussed at the beginning
Yes, sir.
that the matrix inequalities we can express in that particular form. And in static output feedback case, we can't express this as an LMI problem. This is not an LMI problem, though many of the control problems that can be transformed or can be represented as an LMI problem. But when you consider the static output feedback problem, in fact, many of the control problems you can represent as a static output feedback. I've shown one demonstration today. This problem is not an element. No way you can make it an element, right? So then how will solve this problem? This problem is inequality problem, and this will be known as an NP hard problem. You cannot get any solution get a solution very easily. So how you can solve? Then you can do it iteratively, possibly. That is one of the approach. There are several other approaches. Iteratively means you can think of that you can solve one variable once, then solve the other variable other time, right? So once you take a value for this p, then this k would be consisting of k as a variable. That part which will be an element, right? So that you can solve very easily as in convex optimization problem. So instead of this p and k that is more flexibly chosen by iterating over this x by using a particular inequality, and that way iteratively you solve this problem using LMS. So that's what they call it, iterative LMS. Is that fine? Hello. Mr. Naga? Yes. Not audible.
So,
Sir, I'm audible, sir?
Yes,
Yes.
yes, audible. So is that clear?
Yeah, yes, sir. Yes, sir. That
So,
Riccati equation, A transpose P. What is mean by P, sir? P transpose the positive definite function or a planned transfer function?
yes, yes, positive definite matrices.
Okay, sir. Thank you. The last doubt is for better understanding, for referring the LMI procedure, or if you any have any black diagram for LMI, sir?
There are books, several books. You can go for that famous book of 94 by Boyd and Balakrishnan.
Okay,
There are
sir.
4 authors. Linear matrix inequalities in control.
Okay.
Okay. There are several other books that come up and several online tutorials are there and so many. Okay. I just given an overview as a starting point. If you find interest, please go through. There are enough material in internet.
Okay, sir. Thank you, sir. Thank you.
Okay. Thank you. Thank you.
Hello, sir.
So participants, if any other questions are there, we can just take up quickly. Otherwise, we can take through
Hello.
email. Yes.
Hello.
Please.
Yes, Shashovan.
Sir,
Yes.
sir, I have one
Good evening.
query.
Sir. Yes, sir. Good evening, sir. Sir, it was a nice session delivered by you. Sir, I have one question from this concept of this state feedback controller. Sir, can you define the definition of stabilizability and detectability?
Stabilizability.
I mean,
Okay. So obviously we try to do it controllability and observability, right?
yes, sir, yes, sir,
The
yes.
controllable and observable system we study in textbooks. And obviously the extension of that is that stabilizability and detectability. Stabilizability is that the uncontrollable modes must be stable, right? Understand this, the uncontrollable modes must be stable. So it is from stability point of view, we're trying to stabilize a system. So when you are trying to stabilize, if some of the states or modes particularly, I would say, since we try to control the modes or the characteristic equation of the system, if some of the modes are not controllable, then won't we control the system? So still we can stabilize the system. If unstable modes are at least controllable, if we can place the unstable modes, then obviously the overall system remains stable. Though we won't have any control over the uncontrollable modes and we cannot place them, and that affects the system performance, right? And obviously that leads to pole zero cancellation if you go for linear system and transfer functions. Means if you have uncontrollable or unobservable modes, then if you take the transfer function, then you will get the pole zero cancellations, and such pole zero cancellations should be done over stable modes, right? If those modes are stable, then you can continue or control the remaining portion of the system rather than discarding to control it. Same
Okay, sir.
thing for the detectability.
Yes, sir. Yes. Okay, sir. Thank you, sir. Thank you.
Okay.
Thank you,
And
sir.
you can decompose the system in the controllable and uncontrollable portion as well. There are well established algorithms, even routines are there in MATLAB. You can try out them. So that's
Yeah, yeah.
very easy to do.
Yes, yes.
Thank you.
Thank you, sir.
Yes.
Sir, I have one small query.
Yes, Dr. Ankit.
Sir, I think in the block diagram, the motor is running on a sinusoidal waveform instead of those PWM signal. Is it so?
This one you want to say?
Yes, yes. No,
Yes.
no, not this one. Not this one. That was this one. This one.
This one?
Yes, sir.
So please repeat your question.
Sir, the motor is running on a sinusoidal waveform here?
Yes, this is an induction motor. You have to give an AC supply to this.
Okay, so there is no DC to AC converter connected over here to the induction motor.
Okay, induction motor, that is very easy to run but difficult to control. Okay, so induction motor has benefits. One of the major benefit you can say corresponding to compared to other motors, it's that it's very easy to manufacture and it's very cheap compared to other motors, right? But then the difficulty arises when you try to control the motor corresponding to different speed levels and different torque levels. That control is much more difficult compared to if you consider DC motor, right? DC motor, the control is much easier in the sense they are independent. If you want to control the speed, then you control the armature current. If you want to control the torque, you can do it through I, right? The field current. These are clear cut. Then for induction motor, this is so nonlinear and so complex that control is difficult, right? But still the induction motor always run on an AC supply, right? So how we can do that experiment or can generate that variable AC supply or AC supply that is a particular frequency but having variable voltage magnitudes that you cannot generate from the power supply, right? That is fixed magnitude. So what you can do, you can use a rectifier and inverter arrangement so that the inverter can be controlled in such a way that the voltage across or applied to the motor that can be regulated. Okay, so this is basically
yes, sir. Yes, like I got your point. I have just a small query in the block diagram itself. Now I got your point. No problem.
Okay.
So I found this is a very, very interactive session. A lot of questions were asked by the audience. It seems it was very useful and interesting to the audience participants. Thank you, participants, as well as thank you, sir, for delivering such a nice lecture, and also thank you for giving answers so in a so nice manner the various questions raised by the participants and giving your time, valuable time to us. Thank you, sir.